Well, now we come to the real meat of chapters 1 and 2 on stratospheric chemistry, and that's really our discussion on the creation and destruction processes for ozone in the stratosphere. Now we'll start with the creation of ozone in the stratosphere, and it'll be helpful to refer back to an earlier scheme that sort of illustrates the air pressure and temperature inversion that occurs in the stratosphere. And you'll notice that I've labeled a couple regions here with some information regarding the state or form of oxygen in those regions. So above the stratosphere, you notice we have primarily oxygen in the atomic form. In the stratosphere itself, we have oxygen existing primarily as O2, but then also as ozone. But with it specifying that the concentration of O2 is always much, much greater than the concentration of ozone. And then below the stratosphere, oxygen exists really only as O2. Now, where does this come from? How do we sort of work through this? Well, another figure that might be helpful is a plot here of the relative UVC light intensity as we go above the stratosphere and down through the stratosphere. And what you'll notice is that above the stratosphere, we have a high relative amount of UVC light, but then in the stratosphere, a lot of that light is getting filtered out, so that by the time we get to the bottom of the stratosphere, essentially all of the UVC light is been filtered from the atmosphere. And we also have plotted on this graph a depiction of the production of ozone in the stratosphere itself. And you'll notice that this occurs at the greatest extent here in the mid-stratosphere. So let's sort of break down what's going on in each of the regions of the stratosphere and above and below the stratosphere, and sort of relate that back to the description of oxygen and what form it sits in the on the graph on the left. So let's just first look above the stratosphere. So above the stratosphere, you'll notice the air pressure is extremely low, which means that any molecules that are present of O2 are very, very isolated from any other molecules. And so what the primary reaction that occurs is not going to be between molecules, but we get photochemical dissociation of O2 by UVC light. We can calculate the wavelength required for that, and essentially that will absorb UVC light, filtering some of it from the atmosphere, but it splits O2 into single monatomic atoms, just isolated by themselves. And because the air pressure is so low, those atoms really don't run into another molecule for a long time. And so all of the O2, because the UVC light intensity is high, the majority of the O2 above the stratosphere exists only as single oxygen atoms. Now, as we start to get down into the stratosphere, however, then what we see is we still have this photochemical dissociation of O2 into its individual oxygen atoms. And both above the stratosphere and in the upper stratosphere, when those oxygen atoms run into another oxygen form, it's primarily going to be another single oxygen atom. And so really the main reaction that occurs both above the stratosphere and in the upper stratosphere is simply recombination of oxygen atoms to reform O2. And this dissociation and the reforming and the redissociation is a large contributor to the filtering of UVC light from the atmosphere. But then as you start to get into the upper and down into the mid stratosphere, now the air pressure is increasing. And so occasionally those single oxygen atoms will encounter a molecule of O2. And when it does that, then there will be the creation of ozone. Now, in the upper stratosphere, that is a minor reaction simply because the air pressure is so low and the oxygen atoms tend to find each other before they run into a non-dissociated molecule of O2. However, as we hit the mid-stratosphere, the UVC light intensity has dropped off enough by filtering from the regions above the stratosphere and in the upper stratosphere to the point where we have less dissociation of O2 occurring, and additionally we have a greater air pressure, so there are more O2 molecules around, And so we will still have some we still have a sizable amount of photochemical dissociation of O2 into individual oxygen atoms, but those oxygen atoms are now more likely to find an O2 molecule before they would run into each other. And so we now have the formation of ozone by a single oxygen atom combining with O2 to form O3 being the major reaction. We can see that graph here with the relative ozone production that reaches a peak somewhere in the 25 to maybe 35 or 40 kilometer region is the majority of ozone production. Now that varies by latitude and some other factors, but that's a general depiction. And then as we start to get into the lower stratosphere, now the UVC light intensity has dropped off much more. And so I didn't really know how to depict this best, but essentially we have a decrease in the amount of photochemical dissociation. So I didn't have a great arrow to draw this with. It's not saying that it doesn't happen at all, but it doesn't happen nearly as frequently because the UVC light intensity has dropped so dramatically, having been filtered by all of the reactions above it, above the stratosphere, upper stratosphere, mid stratosphere. Now you're in the lower stratosphere, the light intensity has dropped so much that there's very little photochemical dissociation. And that means that the relative concentration of individual oxygen atoms is very low, which means that the essentially the relative rate or relative ozone production also drops off because those individual oxygen atoms are necessary for the formation of ozone by recombination with O2. Now, once you get down below the stratosphere into the troposphere, the UVC light intensity has essentially all been filtered out. So there is no more photochemical dissociation of O2, and hence we have no ozone production below the stratosphere, in the troposphere, at least at upper regions of the troposphere. We have ground level ozone production, but that's an entirely different process, generally not photochemical at all. Now, there's something else important from a couple other things to point out in these graphs. First is that if you're paying really close attention, you might notice that the ozone layer itself is not normally specified as existing all the way up at perhaps 40 kilometers. It's more centered maybe about 25 kilometers. And the reason for that is that although most of the ozone production occurs in this mid-stratospheric region between maybe 30 and 40 kilometers in altitude, that ozone once formed slowly gets transported downwards. There is some kind of mixing that does occur, although mixing is much less in the stratosphere than it is in the troposphere. But ozone is transported downwards after formation. It's a heavier gas, after all, than either O2 or monatomic oxygen. And so the actual ozone layer itself exists more around the regions of, say, 15 up to about 30 kilometers in altitude. The other thing to point out is this is often referred to as the ozone layer, and you might think that in that ozone layer that the concentration of ozone must be significantly greater than the concentration of other gases, or at least than O2, but it's really not the case. O2 is still by far the dominant form of oxygen in that region. The actual concentration of ozone in the ozone layer never really goes above 10 parts per million, but it is still that is enough to filter essentially all the remaining UVC light, and as we'll get to when we talk about destruction processes for ozone, that ozone also filters out the UVB light that we've talked about as being so responsible for DNA damage and skin cancers. And so it's just important to note that when we talk about an ozone layer, that ozone is still the minority form of oxygen in that region, but it's significantly higher in concentration than it is in the troposphere or in the upper stratosphere. The other thing to point out is that it's actually the formation of ozone that drives the temperature increase in this region. So you'll notice we have this temperature inversion and then an increase until we hit the top of the stratosphere where we have another temperature inversion. And it's actually the formation of ozone that drives this, that drives some of this temperature increase. So if we just look at the reaction, monatomic oxygen plus O2 going to form ozone. If we look at the heats of formation for monatomic oxygen, plus 249.2, and ozone is plus 142.7. O2, remember, that's the elemental form of oxygen, so its heat of formation is 0. Products minus reactants, it's simply 142.7 minus 249.2. We end up with this reaction being exothermic by about a little more than 100 kilojoules per mole. And so since we have a lot of that ozone production occurring here in the mid-stratosphere, all the way down into the lower stratosphere and also into the upper stratosphere, we have then that extra heat, or that extra energy from the exothermic reaction is given off as heat, which then warms the temperature, the overall temperature in the region. Now, it might be important to note that maybe the question might be asked, where does that heat actually go exactly? Well, it's maybe more helpful to draw the reaction of ozone formation in this way, where we've got O plus O2 plus some other molecule. It might be nitrogen or N2 or argon, one of the other gases that are present, going then to form O3 plus, again, that molecule plus heat, where essentially that the excess energy is transferred to that other molecule and then sort of given off as heat in vibrational modes generally. And so we don't tend to draw the formation of ozone or the destruction of ozone exactly in this way, where we've got this extra molecule in there, but that essentially sometimes it's helpful to know that it's there or involved as a way of kind of giving off the heat that's generated from the reaction. So that's kind of a summary of the creation of ozone in the stratosphere, where that comes from and the relevant reactions in each region of the stratosphere and above and below. In the next video, we'll start to talk about destruction processes for ozone in the stratosphere.